Continue. Okay, this is our last lecture day. We have to introduce the topic of magnetism. The typical Physics 2 class at most institutions would be exclusively on the topics of electricity and magnetism. So our magnetism is coming at the end of Physics 2. And I guess that's the classic way to do it. We're not going to spend a ton of time. There's some really good, important, relevant topics for you to at least be exposed to, but we're not going to try to turn you into electrical engineers in this course. This is an introductory survey of topics in physics to give you this solid foundation, I hope. After we talk about magnetism for a little bit, there's not much homework. Let me double check this. Not many homework problems. Oh, there's too many. There's a few homework problems on magnetism. So I will get you ready to tackle those homework problems. And those will be the basis for the quiz next week. Now, here's how it's going to be working. Tonight, after we talk about magnetism, we'll stop. I'll say, hey, do you have any questions from the chapter 21 material? Because we have a quiz on chapter 21 tonight. Next week is, let me kind of swap over to what we're looking at here. Let me move our Canvas page up top and share that instead. So on our Canvas page, all our past weeks and then our current trend. So tonight we're talking about chapter 22 and we will have a quiz on chapter 21 up here. So I will go over any homework questions you have from chapter 21 material before you take the chapter 21 quiz. Next week, I will say, hey, you did the chapter 22 homework, I hope. Do you have any questions on the chapter 22 homework problems before we take a quiz on chapter 22? And I'll put that toward the end of class. But before we do that, do you have any questions from the practice exam? So hopefully over this next week, you'll be able to spend a little bit of time looking at the practice exam for the chapters 18 through 22 material. And it should give you a pretty good idea of how much emphasis I'm going to put on each type of question. So the practice exam, pretend you're taking the real exam, try to do the questions with what you kind of have floating around in your brain at the moment. And if you are like, man, I don't remember how to do Kirchhoff's rules, I'm going to have to look at the key for that, then, you can do that. But, you can probably answer number 2. We have resistance, we have voltage, we want to know current. Ohm's law is V equals IR, I equals V over R. I think you could tackle number 2 with what you would have immediately available right now. As you go through the practice exam, some questions will be easy, some will be more challenging. You will find that all of this material is on the latter half of the course. So we started off our semester with fluids and pressure and thermodynamics and temperature and all of that stuff. And then we set it aside and we got into new material. Exam number 2, our last exam that we have in the course, is on the second half. A comprehensive final exam for this particular course is, just kind of painful because this course is in like 2 separate sections. So we just have the second exam. We don't have a cumulative final. The practice exam is longer than the real exam will be. And the practice exam ultimately has some questions about electromagnets, and we'll talk about that stuff tonight, and what happens when particles move inside a magnetic field, and the acceleration of a proton moving in a magnetic field. So some things that you don't know yet, but you'll have a pretty good idea of after class tonight. So after class tonight, you'll be able to spend some time working through the practice exam, hopefully feel in pretty good shape to ask anything you didn't quite get, any questions you'd like another answer to. Because then, now I got to find my way back to the course. Then the following week, oh, do I go below this? Yeah. The following week on Monday, May 10th, we will have exam 2 on chapters 18 through 22 material. So that night, I'll welcome you. If you have any last desperate questions, I will try to answer those. But then I'll say, okay, hey, you can go ahead and start exam number 2. This is what I'll say on Monday, May 10th. You can go ahead and start exam 2, and I will be here on Zoom chat with you while you're taking that exam. So tonight, a quiz on chapter 21. Next week, a quiz on chapter 22. And then the following week, exam number 2 on chapters, whatever I said it was, 18 through 22. So that's how we're wrapping things up. Hopefully a happy and delightful semester. Also, just to mention once again, if you've lost track of them, and I don't see them on this current Canvas page, so maybe you would have lost track of them, but we do have labs, 3 more labs that are due. Labs 6, 7, and 8, and 6 went somewhere already, but I will find those. But labs 6, 7, and 8, so if you haven't done the labs, make sure you do. Our final exam day is like way toward the end, close to when I have to submit exams. So, submit grades. So I will need all of your work by then. These labs are not overly taxing, so I think you will be able to do them fine. Let me move these 2 labs to our current page. And then I'll put the last one there as well. Paste. Guess I'll make it May 10th. And insert, oh, come on, insert. Course link, do you think? Did I call it a quiz? I probably did. Okay, so on our current Canvas page, if you never did lab number 6, that is there. Lab number 7, lab number 8. I believe that is the end of our labs. And you'll be in good shape. So I think I downloaded the PowerPoint for tonight. Just gotta move it. Oh. Okay. Now I need to make sure you can see it too. Hey, there's this thing called magnetism. You have undoubtedly heard something of this phenomenon. If you're into pretty neat effects that happen in the atmosphere, you can position yourself on certain places on planet Earth, and you will bear witness to the fact that particles, space dust essentially, some space dust has positive charges, others have negative charges. I will mention just briefly, my PhD work was all research that took place with positively charged gas particles or negatively charged gas particles in a tube, and we did reactions and we measured the kinetics of those reactions. But my advisor liked to point out that in any cubic centimeter of air, you will find roughly 10,000 charged particles. That most of the air that we experience as we're breathing is charged particles. Now, 10,000 in a cubic centimeter is still a pretty small fraction for the number of particles of air that there are inside a cubic centimeter, but it's not inconsequential. There are charged particles, and maybe you see air purifiers that are deionizers that are actually attracting the charged particles out of the air, because those would be the things more likely to be carrying contaminants, and oxygen and nitrogen are not likely to be charged, and so so a deionizer can work to purify the air. Anyways, in certain regions of the Earth, the space dust that is charged, positive and negative, tends to accumulate. Why does it accumulate there? Well, because the Earth behaves as though there's a giant magnet at its center along the axis of the Earth. And at the two extremes, the North Pole and the South Pole, that's where you have the highest density of magnetic field lines, and charged particles, ions, are manipulated by magnetic fields. Magnetic fields cause charged particles to move in a certain pathway. And so at somewhere, where you have a decent view of what's going on at the North Pole of the Earth, you can see this swirling spiral pattern of space dust that glows because it's hot, moving inside the Earth's atmosphere with a fair amount of friction. And you see aurora borealis, and it's pretty neat to look at. So this OpenStax book didn't come out all that long ago, but darn it, the technology just looks ancient now, doesn't it? But this is a huge leap over, Walkmans and, portable CD players and whatever. But anyways, all of our technology has magnets at their core. All of our credit cards in our wallet, all of the storage media that we have inside our computer, and any sort of portable device, our cell phone, everything has magnets. So they're not necessarily bar magnets, but perhaps you've held a horseshoe magnet in your hand, or you have things stuck to your refrigerator by magnetism. It used to be a more relevant reference, but not all that long ago. There was a television show called The Big Bang Theory, and one of the characters, Sheldon, was annoying to his peers. And so when they spent some time on the South Pole doing research, Sheldon was desperately in search of a magnetic monopole. And because he was being so annoying, his friends manipulated the data that they were collecting to let him believe that he had actually discovered a magnetic monopole, and he was very excited and stopped being so annoying to them. Anyways, that was funny humor on a comedy show if you're nerdy enough to be aware that there's never been a case of an isolated monopole. So we have positive charges and negative charges, and protons are positive. Why? Because Benjamin Franklin said so, and electrons are negative because Benjamin Franklin said so. There's nothing inherently positive or negative. They're just opposite, and so we picked, or he picked, something to call them, one positive, one negative. Okay, whatever. Magnets, magnets have a north pole and a south pole. It means that they have two opposite poles, and they both exist on any magnet. If you take a bar magnet, like so, this kind, and you drop it on the floor and it breaks in half, you wind up with two bar magnets that each have a north and a south pole. Magnets always have north and south. The north and south of a magnet, this is kind of weird to digest. The north and south of a magnet are related to the fact that the north pole of the bar magnet that you hold in your hand is attracted to what is geographic north. And the south pole, so a magnet or a compass, is attracted to geographic south. Weirdly, what that ultimately means is that the Earth's magnetic field features a south pole magnetic field at geographic north and a north pole magnetic field at geographic south. And as this image indicates, it's not actually like at dead center north. It's off a little bit, and it moves a little bit each year. And I think I've read that there is geological evidence of it flipping every so often. I don't know that there's any particular impact to life on Earth, which way the theoretical bar magnet inside the center of the Earth is facing, but it can change, apparently. So the needle of a compass is really just a permanent magnet that is a north magnetic pole on one end, south magnetic pole at the other, and it will naturally align itself such that what we call the north pole of that magnet is pointing toward the geographic north on planet Earth. If you've ever messed around with magnets, you will find that if you push the North Pole, or the common end of two magnets toward each other, if you do it one way, they're attracted to each other and they click together really fast. And the other way, when you try to push them, it's just darn near impossible to get them to touch. And even if you do get them to touch, if you let it go at all, it automatically pulls away. It's an action at a distance force. If you have had any fun with magnets, you can see that they pull on something, say a paper clip, from some kind of distance. You don't have to touch it in order to pick up the paper clip. You can just get the magnet close to it and the paper clip will move and attach to the magnet by this force that acts over some distance through the air. If you had a whole bunch of compasses and a bar magnet, you could do this demonstration where you are actually seeing, because the bar magnet is really close at hand, it's going to overwhelm whatever the Earth's magnetic field contribution to your compass is going to be. And you will be able to map out what is the magnetic field around a magnet. And what you see, it's similar to what we did with electric fields, that the arrows point away from north and are attracted to south. What we did with charged particles is we had them go away from negative and toward positive. So similar thing, and you get a magnetic field just like we had an electric field. Now, the really weird, interesting thing is that ultimately, if you have moving electric charges, they create a magnetic field. And if you have a magnetic field and a charged particle is moving through it, it will feel a force. So electricity and magnetism are related to each other in that they cause each other. They influence each other. Magnetic fields influence electricity. Electricity causes magnetic fields to exist. It's a weird thing. Here's the Earth again. So when we talked about electric fields, we pointed out that there was a force that acted on a small positive test charge, and that the electric field was part of that. So the quantity of the force was charge in coulombs times the electric field strength, which was newtons per coulomb. And so we could see what would happen with a charged particle given any arrangement of protons and electrons. What we have here, it's 3 dimensions, so it's harder to really kind of deal with. So your fingers are magnetic field lines. This is the right hand rule. So bust out your right hand here. Your fingers are magnetic field lines, and your thumb will be the moving charge, the velocity of a positive moving charge. We just have to pick one. Could be a negative moving charge, and then it would be your left hand or backwards. But your fingers on your right hand are the magnetic field lines represented by the letter B. Your thumb of your right hand at a 90-degree angle to your fingers. Your thumb is the velocity component of the moving positive charge. And then your palm is the force So it's 3 angles, it's 3-dimensional space, but they do a decent job depicting it here. The B's are the magnetic field lines, V is the velocity, and the force, the maximum force that is acting on a moving positive charge inside this magnetic field. Magnetic field's always pointing north to south. Inside this magnetic field will be mutually perpendicular, 90 degrees, 90 degrees, 90 degrees. And that's the relationship always with magnetic fields and electric fields and forces. They're all mutually perpendicular. If the charge is not moving entirely perpendicular to the magnetic field, then we get the velocity vector times sine theta, the angle between the velocity and the magnetic field lines, and that will give you the force. So right-hand rule, velocity component, magnetic field lines, force, and when we quantify it, I don't know why they did it this way, but we can try to fix it here. Annotate. So force equals Q V B sine theta. So B is the magnetic field strength in Tesla, like the car in Tesla. Q is the quantity of charge in coulombs. V is the velocity in meters per second. Sine theta is the angle between the velocity and the magnetic field, theta. And this is a force in newtons that we would be quantifying for this, what's going on in a magnetic field. So this is actually the definition of a magnetic field, which I guess, is related to force and charge and velocity, but functionally, this is the equation that we would more be reaching for to figure out what influence the magnetic field has on the moving charged particle. Clear, close, move on. So this is an example problem. It's a proton. Protons, remember, have mass, as do electrons. And the mass of a proton and the mass of an electron are values that I would give you on a quiz or an exam if you needed to know them. And force, remember, is mass times acceleration. So they told us it was a proton. That also includes the information that there's a certain quantity of mass here that we could look up on our equation sheet. It has a speed 5 × 10⁶ meters per second. The proton encounters a magnetic field whose magnitude is 0.4 Tesla and whose direction makes an angle of 30 degrees with respect to the proton's velocity. So find the magnitude and direction of the force on the proton, then the acceleration of the proton, and then I guess you could do the problem all over again with an electron, which has a mass, but it's different. So again, the force equals QVB sine theta. So it's a proton. All protons have a charge of 1.6 × 10⁻⁹ coulombs. That would be on the data sheet too. Velocity 5 × 10⁶ meters per second. B, magnetic field, 0.40 Tesla. Sine of the angle, 30 degrees. Sorry. So plug and chug, you have a force, and then acceleration equals force divided by mass. That is the mass of a proton. And then everything else is the same for an electron, except electrons have a different mass. So it'd be the force divided by mass of an electron. So I think the answers are on the next slide. So tiny little number, 1.6 times 10 to the negative 13th newtons. Sadly, Canvas just really stinks with scientific notation. So, you be careful when you're doing these problems and you're getting an answer and it's, 10 to the negative 13th, that's a really tiny number, or 10 to the 13th, that's a really huge number. So, just be careful as you're doing this math, because it's going to be weird on your calculator to have 1.6 times 10 to the negative 13th divided by 1.67 times 10 to the negative 27th. Those are just numbers that we're not used to dealing with on a regular basis because they're either so tiny or so huge. So be careful with that. And I will try to have a reasonable mechanism for you to report answers where you're not doing, the number 1 with, 13 zeros after it, because that's really hard to keep track of when you're answering questions on an exam or a quiz. Anyways, so there we go, force divided by mass of a proton. This would be given on the data sheet, 1.67 times 10 to the negative 27th kilograms, or the electron, 9.11 times 10 to the negative 31st kilograms. Really tiny number, but still a number. This was part of my world in graduate school, was deflection of a charged particle within a magnetic field, which is also called magnetic field, magnetic sector mass spectrometry. And I was doing a lot of mass spec in grad school, and it is different kinds of mass spectrometry are truly, the ultimate for all sorts of analytical data analysis, chemical analysis, biochemical analysis in whatever you might do in a lab. So, and it's just what we said before, that there's a force that will act on a charged particle moving in a magnetic field, where we just talked about a different amount of acceleration. So in this last slide, we had a proton and an electron, and those two things with their different masses experience different accelerations. Well, one kind of acceleration from physics 1, I hope maybe you remember, was called centripetal acceleration. And it would tell you how wide a corner something would be taking. And so if we were able to figure out spatially different points on this plate here, we would be able to have a charge move inside a magnetic field, and based on the radius of the corner it took, be able to say what mass that charged particle was. And so the charged particle of a proton, whatever, but the charged particle of, benzene that has a certain mass versus, toluene. Is that a benzene with a methyl group off the bottom? Anyways, that has a different mass. And so if you can do mass separation, you could know specifically or have more evidence specifically for what chemicals are in some kind of mixture or some kind of herbal remedy or pharmaceutical or, you know, blood sample from a patient, you know, all these things you could, if you can figure out the mass of the different components, you can figure out or have good evidence for what those components actually are. So this velocity selector is just another analytical tool for separating out. One new thing that we're seeing right now, so often when we're talking about something in 3 dimensions, the X, Y, and Z axis, here the X's mean that the magnetic field is going into the paper. We're looking at the back end of an arrow that is an arrow depicting magnetic field lines. So the magnetic field lines are going into the paper. The velocity of our particle is going in the positive x-axis. That would mean that the force acting on this positively charged particle would be up in the positive y-axis. Taking my right hand, lining up my fingers for the magnetic field lines into the plane of the paper, tilting my hand so my thumb is the velocity vector for the positively charged particle, and the palm of my hand is facing up. And so I would know the direction for the force acting on this positively charged particle in that magnetic field. Yep, I have a lot of redundant slides here. I'm not sure why. So here's our centripetal force, mv squared over r. The force is QVB. The charge in coulombs, the velocity in the magnetic field. This is a case where it's at a 90-degree angle. So sine of theta is the number 1. And so we don't need to do the QVB sine theta because it's 1. That force is the centripetal force, mv squared over r. And so the radius of curvature for this charged particle inside this magnetic field is mv over qb. Now, if we know B, we know the magnetic field strength, and we know the quantity of charge, and we know the velocity. That's kind of a trickier thing, selecting out specific velocities, but we can do it. Then we would be able to determine the mass if we knew the radius. And we don't need to belabor this point anymore. This is the world of a mass spectrometer, and it's very frustrating and sometimes amazingly satisfying when you can get good data. I don't know how much you've ever thought about this, but when you plug something into the wall, electrons are moving through a wire. If there's resistance and that resistance creates heat and light, you got yourself a toaster. There's a thing that you can have by plugging a plug into a wall. You can get yourself a toaster. But what if you want something more? What if you want to make something move, like a vacuum cleaner? Maybe you want both a toaster and a vacuum cleaner. How do you turn moving electrons into physical motion of the wheels or the, you know, the whatever it does that sucks up the air in your vacuum cleaner? I should have chosen a device that moves that I know a little more about, but sorry, I didn't. But your robot vacuum cleaner that rolls around on the floor and scares the cat. How do you make something move? Well, When you have a magnetic field and you have charge, current, that's the I, current moving through a wire, you get the force. There's a magnetic field, there's a moving charge, and so there's a force, and you can, with some clever engineering design, oh, we didn't need to talk about this yet. Come on, clever engineering design, come up with torque on a current carrying coil. If you could just get something to spin around in a circle, and then you can attach some gears and you can do anything else from there, you are able to create a motor. So I don't know what devices you've ever had in your house, handheld mixer or something, a mixer that you plug into the wall, and if those things ever break, do take some time to smash them to bits and pull out the magnets, because every motor that you have in your house has magnets inside. And the reason there are permanent magnets inside these motors is because that's how we turn the flow of electric current into mechanical work, by getting something to spin around. And so this is the basic concept of a motor. And we do not have to get into this math for you to have fundamental appreciation that there is torque due to a force acting on a current carrying wire. N is the number of turns in the coil, because a single loop of wire with electrons flowing through it isn't going to really seal the deal for you. I is current, A is the surface area inside here, B is the magnetic field, and sine phi. Phi is going to change the whole time, so it's a little more complex mathematically, but let us not worry about it. There will not be mathematical problems on our quiz or exam to do this. We just want to get the concept. And hey, let's go back to the past. We really thought this was the ultimate in technology. We had these compact discs. Music was available on a silver disc, and it would spin around like mad, and there were lasers inside, and it was awesome. But ultimately, the only thing that made that disc spin around was a motor, which included a permanent bar magnet and a coil of wire going around, and it would spin the disc. And based on the disc spinning and where the laser was focused on the little bumps on the CD, we would get digital music. Okay. The other thing to mention is that we don't always have a permanent bar magnet in all situations. If you force electric current to travel in a circle, because current moving in a circle interacts with magnetic fields, if there's no magnetic field there, it will invent one itself. So it's called a phantom bar magnet, because the current, this is like a car battery, the current going in a circle creates an electromagnet. So anytime, and I guess this goes back to an image earlier, there was a movie once a long time ago called The Hunt for Red October. And this was back in the movie was about a time back in the Cold War where the United States of America and the Soviet Union were developing weapons technology to outdo each other. And the Soviets had, in this fictional account, developed a magnetic hydrodynamic propulsion unit for nuclear submarines, and then what? We couldn't detect it with sonar, and it would be really nerve-wracking, and the Soviet captain defected, Sean Connery. It was kind of a weird movie. Anyways, this is an actual magnetic hydrodynamic boat that somebody developed, and all you need is seawater. Seawater is a bunch of ions, positively charged particles and negatively charged particles. The water goes through a magnetic field. Because there is a permanent magnetic field, it exerts a force on the moving particles, and it makes a propulsion unit for the craft. And when you do that, there's no moving gears, there's no moving parts. And so this thing, except for like splashing through the water, would otherwise be silent. And that would be a neat thing, I guess. So electromagnets, charges and wires. The other thing that happens is when you drop a magnet through a coil of wires, it will cause current to flow. So current flowing will create something that behaves as though it is a magnet, that is an electromagnet. Or if you drop the magnet through wires, maybe I have an image of this. If you drop a magnet through wires, it creates a fictional bar magnet inside there, which opposes the motion of the magnetic field. I believe that we will see an image of this. It's near the end. Maybe we will not. Oh. I mention it on the practice exam, and it's something that we would have done in lab. So when you see it on the practice exam, you'll get an idea of what's going on with it. Okay. We have come to the end of new material. The chapter 22 homework is not as short as I thought it might have been, but when you go to tackle the chapter 22 homework, the homework videos are there to help you. Some conceptual questions, so you don't need math to do those, and I'll walk you through those. When we talk about the direction of a magnetic force on a positive charge, that's all the right-hand rule. Just know that your fingers are the magnetic field. So in A here, it's coming out of the page. So your fingers are coming out of the page. Your thumb is the velocity, so the force is off to the left and into the page, and you can figure out each of these. I guess here I am doing it on the board. Maximum force is when it's sine of 90 degrees, so it's Q, quantity of charge, 0.1 times 10 to the negative 6 coulombs, Q, V, 5 meters per second, B, 1.5 Tesla, sine of 90 degrees is 1, so the force is QVB, and you can figure that out. Similar. Yeah. Yeah, I think you'll be able to answer these. And if you're struggling to answer these, the videos are there, and me, maybe in a flannel shirt, will help you get through them. All right. So we have made it to the end of the new material. The quiz on chapter 22 is next week. The quiz on chapter 21 material is tonight. And if you have any questions before the quiz, you can private chat them to me, you can publicly chat them to me, or you can unmute yourself and just ask if that makes you happy. I have everyone muted just because I get feedback and I get confused if I don't have people muted. So resistors in series and parallel, remember that series is truly just adding them all up together. It's just that easy. So RS equals R1 plus R2 plus R3, etc. So 10 275 ohm resistors is really just going to be 10 times 275 or 2,750 ohms. Just that easy. 1 over RP equals 1 over R1 plus 1 over R2 plus 1 over R3. So this one would be a pain to add up 1 over 275, but we can do that. 275, 1 over is 0.0036 times 10 is 0.036. So 1 over RP equals 1 divided by 0.0363. Therefore, RP equals 1 divided by 1 divided by. Did I overdo that? Maybe I overdid that. 0.0363. It's 1 divided by 0.0363. So 1 divided by that is 27.5 ohms. I was a little too excited to do 1 divided by 1 divided by. Anyways, what are the largest and smallest resistances? Clear all drawings. So the largest resistance would be just the 3 of these in series. The smallest resistance would be the 3 of these in parallel. So you could do those same process. Yeah, and I would go through other things if they were on the quiz, but they're not. So I won't confuse you with those now. Any questions before the quiz? Anything you're left wondering about that you're like, oh, is this going to be on the quiz? I'm worried about this. Hearing none, I will direct your attention to our main Canvas page. It is down a little ways. Next week's chapter 22. I know it's here. Chapter 21 quiz. So I will be here with you on Zoom chat. If you have any questions, all the data you need is here. The questions are all here. There aren't many. If you need a hint, I'm happy to hint. Just let me know. Have fun, good luck, work through the practice exam and chapter 22 homework before next week so we can go over any questions you have and get you ready for the conclusion of the course. Good luck, have fun. I'm here if you need me.